So we're going to wrap up today's discussions by demonstrating the performance of different types of collectors. And we'll look at the variation in performance between concurrent and non-concurrent collectors for different types of input under different circumstances and different types of collector behaviors. So as I've alluded to a couple times, concurrent and non-concurrent collectors may perform differently when used in parallel and sequential streams on different input sizes. And the may, of course, is the caveat because it all depends on a bunch of different factors that vary from computer to computer and version of the JVM to different versions of the JVM. Recall that a non-concurrent collector works by merging subresults together. And so you'll have these different threads running, and then one thread will be used to join the results of two other thread collects on intermediate result containers. In contrast, a concurrent collector accumulates everything into a single mutable result container. So if you have merging costs that are higher than synchronization costs, it may be the way to go. And that's because there's no need to merge any intermediate subresults. So we're going to take a look at this example that showcases the performance difference of two different collectors. And we're going to have, here's the collectors utility class. You can see there's a bunch of collectors in here. There's toSet and toList and so on, and other variants of that. And then we're also going to have this thing called the concurrent hash set collector. And this is something that I wrote, which later became supplanted by a deeper understanding of features that were already available in Java. So we'll take a look and see the examples. And what happens here when you run these things is that the concurrent collectors work better as the number of words we're dealing with, as the input size gets larger. So what we're doing, this is the example where we're merging things together that are words from the complete works of Shakespeare, and we're trying to end up with a unique set of the words of Shakespeare by merging everything together. And so as you can see, when we run these tests, when we have just the first 1,000 words of Shakespeare, the differences aren't particularly dramatic. In fact, what's interesting, and this is important to remember, for small n, the parallel solution is actually slower than the other solutions. In fact, the parallel solution is actually slower than the sequential solutions. And the point of all that, of course, is that when n is small, the benefits of parallelism are often low. And why is that? Because parallelism always has to do extra work. It has to split things. It has to combine things. And if you only have a small number of input elements, not having to split and combine will actually be faster. As we start getting larger input, so we're dealing, say, with all the words in Shakespeare, then what we're going to see is that the parallel approach starts to win. So up here, notice the parallel time stream collect to concurrent set. That's the slowest. But as the number of elements gets larger, that becomes the fastest. And the reason why that's becoming the fastest is because it's only got one mutable result container, and all the threads are all merging into that, and there's no need, or not merging, they're all accumulating into that single concurrent hash set. And as a consequence, there's no need to have to do any merging of the results. So when n gets larger, that starts to dominate. You'll also see, of course, that doing things in parallel, even when merging is taking place, is still a win. But you can see that the approach that uses parallel non-concurrent collectors, that's what the time stream collect to set result is. That approach is about twice as slow as the concurrent collector. And you'll notice that both of those are substantially faster than the sequential variants of these things, where there's only one thread. And as perhaps no surprise, when you have only one thread and you use a concurrent collector, that's the slowest of all. And the reason that's the slowest of all is because now we're having to pay the price of synchronization, but there's only one thread of control. So there's no point in doing any synchronization. So in that case, the sequential non-concurrent collector is going to be faster than the sequential concurrent collector. But that's because we're paying the costs of synchronization when it gives us no benefit. So I think these results are really quite interesting, and they demonstrate the richness of understanding why there are different types of collectors and when collectors get used for different types of data structures, different types of collections, how that makes a difference, and how the number of n elements we're dealing with makes a difference, and the use of concurrent versus non-concurrent collectors make a difference. So the whole theme here is really, if you understand all these mechanisms, you're able to optimize your code much more effectively than you otherwise would be able to do. And the example is here in this file. We'll probably look at this next time because we're running out of time today. But it's an interesting example, and it shows the difference in performance between all these different variations.